So, hello everyone, this is József Nagy here and welcome to this live stream where I can finally both show you my screen and talk to you via my audio. So first, hi Sally, I hope you're doing well. So if you are watching, could you just write a text whether the audio is okay or is it too loud or not loud enough? Can you hear me? That would be great. So hi all, I hope that you can join today, and today we will continue with the tutorial case. Okay, great, thank you. So hi Denise, I hope you are doing well. Good, so then, hi Franco. You're also here, great. So then I just start with first steps regarding the tutorial, and then when we are about to start, then maybe I check again the chat. Okay, so last time, what did we do last time? Here is the zip file that I uploaded to my GitHub account from last time. So hopefully you had the chance to take a look at it. So I just continue here with the next step. I'm just going to create a copy of it, and then afterwards I will just upload a second zip file called tut2. And now, so we created the geometry in Blender. No, that's not the correct Blender version, but oh well. So here, there is ParaView. This was the object file that we created. And with this object file, we extruded the mesh. And then this is the mesh that we created, a 2D case with a nicely structured mesh up until this circle. Here I did my own meshing algorithm, and I created a mesh around the circle manually. And now, so this is one cell over the thickness, and now we will set up the case. Okay, so then we can progress. So I took this video as a basis, so it is an ANSYS tutorial. I just want to check whether OpenFOAM can run this tutorial and then do this live with you. So maybe you head over to this video and then hit a like, because it is a rather straightforward video. Okay, so then Ali, hi Ali, how are you doing? Hi Mattia, you made it, very good. So then let's just start. Okay, so I'm just going to mute the video because I don't want to have any copyright strikes. Okay, so now I found the position where he or she, I don't know, starts with the case setup. So now I'm just going to start and then see whether it fits my case setup workflow. Otherwise I just maybe I just open up a Notepad++ and just write down steps that I need later on. Okay, so let's just see here. So he's opening now Fluent, and he's starting with the case setup. So he loads the mesh, and then we come to the models. Okay, so it's viscous laminar. What does that mean? Okay, so and he takes K epsilon model. So viscous laminar means that he uses a single phase solver in Fluent, but it is viscous plus the turbulence model, and he uses the K epsilon, the standard K epsilon model, which means for me that I'm going to copy a tutorial which uses the K epsilon model, the standard K epsilon model, with standard wall functions. And he uses the default model constant, so we will not change that either. That would be overkill for a tutorial. Okay. Good. So before we continue with the fluid, let me just start. So I'm here in live, so I just go into tut2 and I just create a case folder. Okay, so here in case we don't have anything. So now I copy an existing tutorial of OpenFOAM version 2012 before I forget. I just source my version 2012. I have an alias for that just to be faster. And now let's just see what do we have here amongst the tutorials which would fit as well. So tutorials incompressible, and then I want to use going to be a steady state case, so I will copy something from SimpleFOAM, and I think the good old Pitt's Daily tutorial will serve us well. Let me just check the turbulence model. It's K epsilon, so great. So we have now a case. So this is how you set up K epsilon, viscous case with K epsilon. You find an existing case and copy it. If there is nothing, then you have to modify it. Okay, so then it was very easy to set up now the K epsilon model. Let's see. Yeah, and we here are already templates for the wall function. We use the standard non-rough wall functions. And now for the fluid, we don't open the Fluent database. We will do this manually. We use voter, and this is the later point where we use we open up transport properties. But actually, I could just open up transport properties. What would be the best way to do this? Maybe if I go here to tut, case, constant, and transport properties. Here is the viscosity. Okay, now how do we come here from the combination of density divided by viscosity to this new? So SimpleFOAM, and I'm sure that also in Fluent it's the same. It's just that the GUI does this calculation for you. So we have to divide the dynamic viscosity of 0.001003 by 998.2. So let's just do this real quick. How to do this? I guess I'm 001 and 003 divided by 998.2. Yes, so I did the correct calculation here. Yes, so this is now our viscosity here. I'm just going to paste here. So this is 10 to the power of minus 6 plus a little bit behind, so we could use just one e minus 6, but oh well. So that was easy for the case setup, and we can must not forget that because we are using SimpleFOAM, the pressure is not the pressure in Pascal, but rather the pressure divided by density. So when we evaluate the pressure in ParaView, we have to multiply it with 998. Maybe I just write this down, this calculation here, just to have it in our mind that we have to multiply the pressure by 998.2 to get the pressure in Pascal. Okay, so that's maybe one important step, but oh well. So now let's continue with the video here. So we just loaded our database manually. Okay, cell zone conditions. Okay, we don't need that. We want to use, we already did that. We don't have aluminum, that's just a rigid wall. Okay, and now the boundary conditions. So this is now where it starts to become interesting here. Case 0. Okay, so first things first. In 0, we do not need the new tilde model. This is for the Spallard-Almaraz model, and we do not need the omega file because we are not using the K omega model. So this is what we end up here. So it's 5 files that we have to modify accordingly. Okay, So let's just see what we start with. Okay, so the inlet. Do we do the inlet? Okay. Very good, zone name, inlet. Now we start with the inlet. Okay, so how do we know what were the boundaries? Either we check it in ParaView or we check it in our polymesh folder. But actually we could just copy here polymesh to my case, and then we immediately imported the mesh, and then in boundary we have the names here. Okay, so our inlet is called inlet, our outlet is called outlet. Then we have the empty front and back planes, which we have it all out of the box. Very good. So there's something that I think about last time. So we have two walls called pipe walls and circle, and then we have our inlet and outlet. Okay, so now we are concentrating on our inlet for the velocity, for the pressure, and for the turbulent values. Okay, so let's use the same values. So here it seems it's important here to specify the turbulence values in a specific box here, and we will define the turbulent intensity. Okay, so we have a velocity magnitude of 0.25. So we will just use 0.25. Maybe let's just check the direction. Let's just create the open.foam file here, and which is now just an empty text file. Okay, and our inlet should be here on the left hand side, which it is. Okay, so we can now assume a velocity in the positive x direction of 0.25 meters per second for the inlet. Good. Then the same, no, let's just watch this. Okay, so the turbulent intensity there, okay, he does some comments. There is this rough estimation for the formula that you can derive it, so we will just use the same turbulent intensity that he uses here. Okay, so now we use a turbulent intensity of 4.51, and this is our K value, and now how to specify it. And this is something that I usually never know by heart. So for that I always have to cheat and open up the boundary condition itself. It's in SRC finite volume fields FV patch fields derived, and then turbulent intensity kinetic energy inlet. Why do I know that by heart? Because I have taken a look at this header file a lot of times, because I cannot remember the correct syntax. So this is the correct syntax here. So I'm just going to select it, right mouse button, which copies it, and I'm just going to paste it with Ctrl V. So the boundary condition is turbulent intensity kinetic energy inlet. And here now we define the turbulent intensity. So it's 4.51%. So we have to here write 0.0451. And we have some initial value. I really like to use 0.1 as first value, but let's see what he uses for initialization. I really like to use 0.1 because it usually works as initial value very well for most cases, and then of course it is calculated. Okay, so this is our inlet. Now our epsilon, where we specify this hydraulic diameter of 0.1, which is the height of this planar 2D case, and this boundary condition is unfortunately at another point, and I believe it's in turbulence models, and then is it here? No. Okay. let's just look for it. Find dissipation rate. Okay, no, that's not. Okay, so here it is, turbulent mixing length, dissipation rate. Okay, so it is in it was in RAS. Oops, that's not what I wanted. Okay, mixing length, dissipation, mixing length, dissipation inlet. So this is for epsilon. Yes, okay, and now this is the boundary condition, the name, and then we have the mixing length, and then a placeholder for the value. So this is just an initial value that is going to be recalculated. Okay, and now the mixing length was 0.1, so that's perfect. Just going to use here also 0.1, and let's see whether he will change this. Okay, so that is our inlet. Our inlet is usually calculated for the new t value. So it is either calculated or it is a Wall function. And for the pressure at the inlet we use zero gradient, and then that's perfectly fine. And in ANSYS Fluent, as I can see, there is no boundary condition that you define, most probably because they use the equivalent pressure boundary for a fixed value inlet boundary condition. Okay, so yeah, very good. So the fully developed flow, that is what we're doing. Okay, and now the outlet. Let's see what he uses for the outlet. So I guess we use an outlet pressure of 0. It's called gauge pressure, but I usually like to use to call it atmospheric pressure. And so we cannot specify the turbulent intensity at the outlets. There is no such boundary condition. So I'm just going to do the next best thing, because here you can see the backflow turbulent intensity. So we can specify, so as I suspected, we use a gauge pressure of 0, so this is what we are doing also with this boundary condition. At the inlet we just using this, and then so where we specify the velocity, there we also specify, there we use 0 gradient, and for K we are using at the outlet, and now I'm just going to use inlet outlet. Why do I use inlet outlet? Because because here he assumes a backflow, and then a backflow possible intensity. So what you can do, we can specify the inlet value. So I'm not sure about this, whether 0.1 will work. What we could do, just use dollar internal field. Possibly that's the best approach if we don't know the backflow rate. So it just should take the self-center value. If we have a velocity that is pointing inwards. Okay, so at the outlet we currently use 0 gradient. Am I satisfied with this? I'm not so sure. So this is a very simple boundary condition. Here we could inlet outlet, use also inlet outlet, inlet value, and then say 0, 0, 0, and then 0, 0, 0. So this would be the boundary condition where we want to suppress a backflow. Okay, so there is a comment. So hi Rupayan. So I'm going to try to learn OpenQBBM to model. I'm not getting suitable. Can you please help me how to learn it? So OpenQBBM is a very specific model, so it has nothing to do with this tutorial. So maybe you just write a comment somewhere below a video, and then we can start discussing, but that's not the goal of this that's not the goal of this tutorial, so that's for a different conversation. Okay, so with this boundary condition we suppress the backflow. We could use pressure inlet outlet velocity, where we do not need the inlet value, and this would allow some backflow. So maybe we use this. So I don't know whether we are going to have a backflow. I don't think so, because it's a very long geometry, but oh well. So I'm just going to use this boundary condition on the outlet. Maybe we can see, maybe the inlet outlet boundary condition is a better idea. Okay, so for the outlet I'm using here the gauge pressure, it's calculated, and then we have inlet outlet, and at epsilon is also inlet outlet, although this is overkill if we used this inlet outlet, because this suppresses every backflow, so then we will never use an inlet value. But because we are using the pressure inlet outlet boundary condition, this is something that we can use here. Okay, so these are the inlets and outlets. So as I mentioned, we cannot specify the backflow turbulent intensity, only the value. There is no such boundary condition. Maybe that would be an idea to implement such a boundary condition. Okay, and now here we are using on the pipe wall the standard wall function without any roughness height. So this is just a typical wall function, and yeah, so is there some information? So he does not use wall 4, whatever wall 4 is. Yeah, so we use the wall functions on pipe walls. So I'm just going to rename upper wall here in all files. So K and newt P is going to be 0 gradient, upper walls, yes, so and then save, and then I'm going to use circle here for lower wall, save, circle lower wall, circle lower wall, circle lower wall, and okay, so this no slip boundary condition is nothing else than fixed value 0, 0, 0. I hope that you know this by now. Okay, so these are now actually all the boundary conditions, because we already have this name for the z direction to have it's not to solve in the z direction, because we are in 2D here. Okay, so now let's just see. Okay, so now we are at the solution methods. And now here we see that he is using the simple algorithm, which means that we have to start simple foam. And then let's see what can we do here with the within FV scheme. So time resolution is steady state. Then the gradient scheme is least squares. So here I can just least squares. So the default is usually Gauss linear, which let's just try least squares in OpenFOAM. Then pressure is second order, which is I believe this part, and so we don't need omega, we don't need this. Okay, so turbulent kinetic energy is upwind, upwind, so I'm just going to switch this to upwind. Okay, and then he just changed the momentum, which is u, to second order upwinds, and then this is linear upwind grad u, so that's perfect. Do we have here something else that we can change? No. Okay, so under relaxations, which is in FV solutions, here we could have some under relaxation, so the pressure is 0.3. Pressure is usually under fields, 0.3. Then let's see. Okay, so he does not change here the default values, so let's just use here default values. So we don't have any density or body forces, the momentum and the turbulent kinetic energy. So momentum U is 0, and then everything else is the turbulent kinetic energy 0.8. Okay, so monitors, residuals. Okay, so here we can set, so it's 10 to the power of -3, and I believe he changes this to 1e minus 6 and uses it everywhere else for epsilon, k, and the velocity. Okay, copy and paste is a good idea. Okay, so continuity. Okay, 10 to the power of -6, so we can do that. So let's just use here also for the relative tolerance everywhere 10 to the power of -6. We don't need these entries, just UK and epsilon. Very good. And residual control, this is the question, when do we consider it to be convergent? Let's just say 10 to the power of -6, so which most probably we will run until end time. Okay, what is paration? No, that's just pressure. Okay, so that was some copy paste error here, so let's just save it. And then solution initialization. Okay, so let's see, what do we use here? Okay, so for the pressure we are initializing it with 0. Very good. The velocity is 0, 0. So this is also what we are using here. That's also perfect. And we are using a very interesting value for the turbulent kinetic energy, but let's just use this. So it's 0.000. This is very, very low, so I'm not sure whether OpenFOAM will converge with it, but let's just initialize it with this value. Oh well. So this is K, and epsilon we have 6e minus 0.1811 6.65. Okay, and then let's just initialize everything else also with this very low epsilon value. Okay, so initialize and then rank calculation. We want to have 1000 iterations. Okay, and now we could start. Okay, so 1000 iterations. This is what we will set also here. Instead of 2000, just 1000, and we will write every 100 iterations. Okay, so I believe that's it. Good, so are there any questions? Talking about the content of the video, do you mind you explain a little bit more what's behind the calculated BC for nu-t? I'm happy to do so. Okay, so what is nu-t calculated? So nu-t, let's just talk about K and epsilon. So for K and epsilon you solve a partial differential equation. But those are only auxiliary fields because you calculate nu-t out of those values. So maybe I can just show you here. So instead of going to the derived fields, here is the K epsilon model. And let's just see. So here you can see. So in the source code, nu-t is CMU, which is one of those constants, multiplied by k to the power of 2, so squared divided by epsilon. So you transport those values with your fields, k and epsilon, and out of those two you calculate nu-t for all the internals, for all your cells. Now the question is, how do you treat your boundaries? And then there is this additional line here, correct boundary conditions. Now, and this means that this wall function is being loaded for on the walls and also for new t, and everywhere else, no, sorry, so for new t, the wall function is used on walls, and everywhere else this equation is being used. So this is then how it is being calculated on the inlet and outlet according to this equation, just like you would do it in each cell. So this is this calculated boundary condition. So you can only use calculated for values which you don't transport. So if you have your iteration number, then you have solving for ux, solving for uy, solving for p, solving for k, solving for epsilon. For those you cannot use calculated because there you have to specify your boundaries, but for values that you calculate out of those transported values, you can use this calculated boundary condition. So I hope that this helped a bit. Okay, I want to do the simulation of flow of micrometer sized particles in a microchannel. What should be the approach? Well, this is more a Q&A question. Well, there are Lagrangian solvers, so I would advise you to check out the solvers for Lagrangian flows. Then Turbo Tommy, hi József, thanks for your uploaded tutorials. You're welcome. You suggest in one tutorials the Blender add-on from Rheologic. Do you know an alternative? Yes. So this was for older versions. Check out one of my. I can just show you here. So this, you're not the first one who asked this. So here is this tutorial, how to hack Blender for OpenFOAM. This is the alternative for that. Okay, so it's just a very short 1 minute video. It is very, very short and does the same thing. So why k value is surprising? Please explain. So you mean why is this value? Because it, in my experience, k is higher than 10 to the power of -4, but we will see. So I'm not saying it's wrong, it just surprised me. But we will see whether it's correct or not correct. Okay, so let's just, okay, so now he is starting the simulation. Iteration 1 through 1000, so at 2630 he's starting and he's stopping at 1.5, so 1.5 minutes to 2 minutes is what the simulation took. And so now let's see whether SimpleFOAM just runs. Okay, so it runs. Let's see how long it takes for SimpleFOAM to run. Okay, so we are now at 100 iterations. So let's see whether we can beat Fluent, although we do not have the same number of them. So it's not the same mesh, but still, if we can come to 90 to 120 seconds, then I'm a happy camper, because this means that we are as fast as Fluent. Okay, and we already converged within 500 iterations, so that's great. So if we compare now, so if we double the calculation time, we are still faster than Fluent. Awesome. So as you can see, so these are what I meant before, the transported values. So we calculate ux, uy, we transport it with the Navier-Stokes equations, we have the pressure equation, and we have epsilon and k, and out of these two we calculate nu t. So for k and epsilon we cannot use the calculated boundary condition. Okay, so that was fast. Okay, so let's just quickly possibly reload it. Okay, so and let's just see what happens here. Okay, so let's see 100 iteration, 200, 300, 400. Great, so the velocity does not considerably change between these two. How about the pressure? Pressure is constant, very good. Then pro tip, so a very good estimator for convergence is this nu t, because it is calculated out of k and epsilon, so both k and epsilon and then the underlying velocity field have to be convergent for this to be nice. And as you can see, it does not change, so this means that the flow is nicely convergent. So our inlet value was too high. So what do we see here? That is that the nu t value is 10 to the power of minus 4, or physical nu value of 10 to the power of minus 6 is at least 2 orders of magnitudes lower, which means that our flow is fully turbulent. So that's nice. Okay, so there is the velocity field. Now let's see what do we have here regarding pressure. Okay, so it's somehow turned around, so let me just turn around my, so here so here seems to be the inlet, which is weird. So let me just rotate this, and I never know which one it is. 90 degrees, that's the wrong one. Okay, so minus 90 here. Okay, so now this is it. Z direction. Ah, come on. Come on, minus 90. Now we have, okay, so now we have here the same values here. And if you want to compare, don't forget we have to multiply the pressure with 900. We should have the same order of magnitude, so it's between minus 100 and plus 100. Let's see what do we have here. So here he sees minus 150 and plus 60. So I'm not sure whether this is due to mesh convergence, but it is at least the same order of magnitude. And from the flow pattern, it seems to be the same. What I am not 100% sure about is, okay, so it is converging towards 0. So here he sees somewhat lower pressure values on the top and the bottom. Maybe we could, if I refine the mesh here, so feel free to refine the mesh and add some layers here manually, and then see whether you can get a better value for the pressure minimum here. But qualitatively it's the same. So now let's see the velocity here. So which is very similar. Let's see. So here the maximum is 0.6. For us it's 0.56. So I'm perfectly okay with this for a tutorial. And he even uses the interpolated values, so which even lowers it a little bit. But I'm perfectly fine with this. That's an error of 0.3, so it's less, it's around 5% error between his tutorial and my tutorial. That's perfectly fine. This looks like a good agreement to me. Turbulent kinetic energy. Now this is something that I am very interested in. Okay, so our inlet value is, so this is what, okay, so it's 0.0014 is the turbulent kinetic energy in this region. So the minimum is, let me just see, okay, so so we specified this turbulent kinetic energy, so it is assumed to be very small. Okay, I now just say that's a correct value, so most probably it was fine-tuned. So our initial value was okay. As we can see now here, due to this disturbance, due to this circle, we have now higher values of k. So my value of 0.1 would have overestimated this value anyway, so I'm perfectly fine here. So, and now he has here a value of 1 to the power of minus 2. So, okay, so we have here somewhat higher, so it's 0.018, and he has here 0.0106. So it is a bit lower, and also his detachment is not as long, but qualitatively it looks very similar. As you can see here, the maximum does not match, but it's okay from my point of view. Okay, what do we visualize now? Okay, come on. Okay, velocity vectors. That's of course something that we can do. So we are using arrows, orient them with the velocity, and we do not scale. Okay, this is much too big. Okay, so now this looks better. Okay, so here you can see the nice flow, and then the backflow here. Yeah, so we can see the same behavior. We can of course color it with the velocity. No, we cannot. Okay, that's bad. But here, I mean, of course I can color it if I use another calculator. Maybe that's also a trick for you. So if I just use square root, and then the x component plus the y component plus the z component. Oh, so it's okay. No, let's just call it vel. So it's just really the velocity, not as a vector, but just as a scalar. And now, I hope that we can now color it with the velocity. No, we cannot. Okay, so I'm not sure why. We really should be able to, but oh well. Okay, so this is what now the flow looks like, and this also looks very similar to what we see. So qualitatively it's fine. Most probably we have to do an actual validation here. Okay, so Lina closes fluent. I'm not sure. Yeah, and then streamlines. So as you may have seen it, I left this function here, which then produces in post-processing streamlines. So now on the streamlines, do I see any streamlines here? Okay. I did not use the correct, I forgot to use the same correct values for the streamlines. Sorry about that. So we'd have to change the start and the end, but we can try and quickly do some streamlines here. But I find that the ParaView streamlines are not the best. So we start at 0.5, no, minus 0.5, minus 0.5, and let's just 5, so let's just put it into the center, and let's just use maybe 20 streamlines instead of 1000. Nice, nice, nice. And now again I have to just roll this. Okay, so now we have here the streamlines, and here I can, for whatever reason, visualize the velocity. Don't show the line. Okay, very good. So here you can see that we have almost the same streamlines as he has. Nice, nice, nice. We cannot do this, but I'm not sure why we would use these balls. Okay, save this picture. Okay, and now it's about saving the picture. Okay, one last thing that I want to mention is that these lines are very thin. Alternatively, you can go to, so not alternatively, additionally you can go to filters, alphabetical, and then here is tube, and then press apply. So this adds tubes, but of course these tubes are too thick. Yeah, so with this you can change the thickness of the tubes, and then these are sometimes better than just the lines, just for visualization purposes. So this I prefer the tubes compared to lines. Okay, so that was the tutorial. I am first glad that OpenFOAM was faster, but I'm not sure, maybe my laptop is newer than his. I mean, it is out of 2017, so possibly his laptop is a bit slower, but at least OpenFOAM is in the same order of magnitude. It seems to converge faster, so because we did not need the 1000 iterations, and qualitatively we do find the same order of magnitude for k, epsilon, k and velocity, as well as the pressure. There are small changes. Maybe if we had access to the mesh, then maybe we would get the same results here. So feel free to download this tutorial, play around with it, change the mesh, and then run it. So this was it that I wanted to show you. So we successfully set up the case and ran the case. It was not very difficult, so you can do it very easily. Just start with the entries in 0, then constant and system, and it is just a straightforward setup. Okay, so before I talk about my next plans, let's just go over to the questions here. So we can hear you. You are missing in the outlet value. Okay, did I miss it, Franco? Where did I miss for outlet? I'm not sure where I missed the semicolon, but okay, maybe just right below. Talking about the content. Okay, so I just skipped you. Sorry, Franco, that I skipped your previous comment. I want to do the simulation of flow. Okay, we already had this. Y is K. Okay, hi Nidal. Is there a way to get average values of a batch number of slices in internal, doing it manually? I'm not sure what you mean for batch number of slices, internal geometry. So you mean rather than, where is my mouse? Rather than, for example, putting a slice here, and then do the integrate variables, do it every time manually. Can you do it? Yes. So there is the can you see me? I think that you lost me. No, you didn't lose me. Okay, so for whatever reason, it seems that my YouTube... So can you hear me? Can you see me? Please just write me a message, because my YouTube seems to be crashed. Can you hear me? Did I lose you, or am I still online? Okay, very good. So sorry about that. So okay, so sorry about that. Okay, so so back to Nidal's question. So yes, there are function objects to do that, where you can define, for example, STL files, and then you define the STL files, and then it will automatically output the values. So you can do that. On Patreon, I do have examples for not the STL models, but how to use the function objects. Thanks. Hi Manos. Any suggestion of any solver for plasma flow inside a tube? So real plasma. So that would be something very highly viscous and multiphase, or I'm not sure. So it would be, if it is multiphase, then interfoam. If it is single phase, then just pimple foam. But you need most probably non-Newtonian fluids. Okay, so then Mattia, very clear, thank you indeed, you're welcome. Luis, hi Luis, do you have a tutorial on how to plot residuals as it is calculating? I do have one on Patreon, not on YouTube. Luis, excelente, okay, excelente. Which one is good for meshing, Salome or Blender? Well, in Salome you can directly mesh and then import the mesh to OpenFOAM, but it is not hex dominant. It is. I'm not a Salome expert, so I think some of the viewers have more experience in Salome. In Blender, what I do, I mesh it manually, export it as an OBJ, and I extrude it for 2D cases. Sometimes it even works for 3D if you can extrude it. So it really depends on the problem. Hi Lou, Raphael, hi Nidal. I mean, let's say 20 across the flow direction. Yeah, so instead of having the 20 slices in ParaView, you can have function objects, which then 20 STL files, which then you load as function objects. Luis, yes. Nidal, yes. Okay, so this was my hiccup from before. Dennis, my question is, does wall roughness only defined in Nuti file? Yes, there is only the Nuti rough wall function where you can define the roughness of the wall. Nida, thank you, Manos, thank you. Okay, so then that was it. Okay, let's come back to my next steps. So because we now finished this tutorial, and it's now 1 hour over, so next time maybe I will create a 3D mesh with a sphere, and then create different kinds of meshes, maybe with Snappy, maybe with CF mesh, with layers, without layers. Let's see whether we can get layers involved with a sphere, and then run this problem for a 3D case. And then we can compare the CD values with the theoretical curve. And then I'm not sure how many Reynolds numbers I can run in a live stream, but then after next time, or maybe after that live stream, then I can run, or maybe you can also run different Reynolds numbers, calculate the CD value, and then see how nicely it fits the theoretical curve. Yeah, so this is something that I wanted to do now for a while. So next time we will try and take a look at a sphere, a mesh around a sphere with Snappy and possibly even CF mesh, and then set up the case again and then run the simulation. So this is now my plan for the next live streams. If you have some inputs, if you run these tutorials and you find something, please let me know below the comments. This live stream will be available as a regular video. It usually processes overnight, so most probably tomorrow. I'm not sure why it takes overnight, but oh well. So, and then we can rewatch it and then try it out yourselves. Okay, so there are possible on VAVT, please. Okay, thank you, sir. Still on. That would be awesome. Looking forward to it. Okay, yeah, so next time I will announce it. I'm not sure, is it going to be next week or in 2 weeks? Let's see, next week. Possibly, or in 2 weeks. What do I plan for next week? Wednesday, 3. Yeah, so either next week or in 2 weeks. I will announce it when, and then you can just join. Okay, so that was it. So there are no additional comments. Then I hope that you enjoyed this live tutorial, and hopefully if you rewatch it on your own pace, you can recreate the results, maybe even improve them. If you do so, make sure to comment below the video and tell me what you improved, or you can also write me an email, and then if you improved your this tutorial, then I'm happy to also share your cases on my GitHub account so people can check out also your improved results. So with that, thank you for watching and listening, and I hope to see you next time.